RAP students, this is Dr. Smith here again. We're talking today about forces in motion for our fifth graders. And I know that you see that I have this soccer ball here. So I'm going to use a soccer ball just to help me tell you a little bit more about forces in motion. So I don't know if any of you play soccer, maybe, maybe not. Usually in gym you get some time playing soccer. I think it might be high school at least. But we're going to talk about the soccer kick, okay? Now, in order to kick a soccer ball, what is it that you have to do? You have to apply a force with your foot to the ball. Okay? So, with our soccer kick, when you kick the ball, you're putting a force into the ball. Now, a force is any push or pull on an object. Now, I'm not going to go in extreme detail with all of this. This is to be a review because we're going to go over some practice questions so that you can make sure that you are ready to answer questions dealing with force and motion and how it relates to objects, okay? So force, any push or pull on an object. So are we pushing or are we pulling? You are going to push on the object, okay? Now once you push on the object, the ball is put into motion. Now, if no other forces act on this ball, the ball will just keep going forever and ever. Does that happen in real life? It does not. But what they call that whole concept of a ball just continuing in motion is actually inertia. As you can see here, it is the tendency of an object to resist change to its state of motion. So if this ball, when this ball was sitting still, let's say on the ground in the grass, before you kicked it, did you have a problem with it rolling all around? No, you did not. Inertia was helping it stay there. If it was still, it's going to stay that way. Now, once it is kicked using your force, now the ball is going to start moving. If there's no other force, it will continue to move. But does that actually happen in real life? It does not. But before we move on, let's say we change this ball to a bowling ball. Now, how does the story change? You go to kick a bowling ball. First of all, you may hurt your toe, your foot, depending on how hard you kicked it. But the change, they're both round, but one is heavier than the other. So when the mass changes, you have to put a bigger force into the ball, okay? So you have to have you have to have greater force when you have a greater mass. And if you're not sure what mass is at this point, let's find it. It's right here. The amount of matter an object weighs. People tend to think about weight. And in this case, I guess it's okay to do that because we know that a bowling ball and a soccer ball are very different. You cannot kick a soccer ball and or a bowling ball like you would kick a soccer ball. Okay? So now let's move on. Let's say that you would like to kick the bowling ball just as far as the soccer ball. Let's just forget about the fact that you may hurt your foot right now. Let's just think about the mass of the bowling ball. So how would the force need to change that you are using to kick the bowling ball compared to the soccer ball? Are you going to have a smaller force to get it just as far as the soccer ball, or are you going to have a larger force? And the answer is you're going to have a larger force, right? Now, if this bowling ball is more, if it has a greater mass, what will the inertia be like if there's no other force working on it but the force that you use to kick this bowling ball? It's going to do the same thing. It's going to keep that ball in motion, right? Here's the thing. The bigger the mass, the larger the inertia also. So you can also say greater mass equals greater inertia. Okay? Now, in this case, in the real world, we actually have other forces that work on the ball. Can you think of what they are? There are two that I'm thinking of. And if you look at the definitions on the side, you may get a clue. Yes, they are gravity and friction. So, gravity is the pull from Earth that keeps objects from floating into space. So this is what keeps us on the ground. Unlike if you were in outer space where the astronauts have to be pretty much buckled in to seats so that they don't fly all over the spaceship. So this is actually the same. This force, this gravity, is actually the same for all objects. It doesn't change. What happens is, based on your mass, the mass of the object, that is what makes things kind of work out differently. For example, other planets in relationship to Earth, they actually have a gravitational pull towards Earth, but because the planets are so much bigger, they don't actually come towards Earth. Now, us, we're a lot smaller, so that's the reason that we can stay on Earth. That's just a little tidbit for you. Every object, everything has the same gravitational force. Gravity is the same. It's just based on mass. Now, the other thing is friction. Now, friction is a force that acts against moving objects. So it's going against whatever it is that you're doing. So if you were to kick this soccer ball in the grass, you're going to have the rubbing of the grass, the bumpiness of the grass, whatever, or if you're somewhere else, whatever surface that's going to cause rubbing and have forces acting against things. And both these things, gravity and friction, they actually cause the ball to stop if you don't put any other force into it, okay? So we always have to think about our other forces, gravity and friction, okay? And they work against the object. Now, the more friction that you have working against an object, you're going to need a larger force to keep something in motion. So, for example, when you're skating, that's a good example. When you skate, do you skate in the grass? You usually don't because you have so many forces working against you. That friction will get you each and every time. So when you're trying to skate in the grass, you have to put forth more force. So it's harder to do. However, if you're at a skating rink where they have a nice slick floor, wood floor that's been waxed or whatever, not as much force to keep in motion, right? So that's a good example to think of. So let's put that one up here. When there's more friction, lost my ball, more friction, you have to have a greater force to stay in motion. Okay. Now, the more force that you put into something, you're gonna have a greater change in movement, okay? So our example, soccer ball. If you want the soccer ball to go farther, you're gonna have to put more force into the ball, right? So it's gonna be more motion. So more motion or movement, let's call it movement. You're going to have a greater force. And what will happen with this movement here is you're going to have increase in speed. So that ball is going to go, once you kick it really hard, it's going to go faster. But what else is it going to do? It's going to go farther. You're going to have an increase in position. Okay? So let's go back just in case some people got lost and talk about the soccer kick again. When you get ready, if you want this ball to kick this ball, you have to apply what to the ball? Force. Now, if there's no other forces acting on this ball other than the force that you use with your foot, the ball will keep going forever. And that would be because of inertia. That's what inertia is. It's over there. However, we do have other forces that act on the ball, okay? The other forces that act on the ball are gravity and friction. Those two things, they actually act against the ball. So that would cause the ball to stop eventually. Now, if you have a lot of friction, that means that you have to put a force into the ball that's a lot more for the ball to go farther and faster. That's the change in movement, okay? That's your increase in force. Now, let's put the mass in there. If this was a bowling ball instead, you would have to put in, because it's a greater mass, you would have to put in a greater force. So whatever you did for that soccer ball, you're going to have to make it even bigger, even greater. And it will have a greater inertia. However, that also means it will have more forces working against it. So I hope that you understand how that works, okay? If not, you need to go back over this again. You can definitely ask your teachers and your RAP family to help you with that concept. But now we're going to apply all of that to a few little calculations, okay? Okay, let's talk about speed. So this is one of the ways that you can calculate the speed. This is something that scientists like to use to quantify or measure things. So speed is the distance something travels in a certain amount of time along a path. So let's say that you kick a soccer ball a distance of 10 feet. And it takes the time that it takes until it stops is 2 seconds. That's pretty good. Okay? You can actually calculate the speed because speed is just distance over time. So if we did that, it'd be 10 feet over 2 seconds. And if we did the division, 10 divided by 2 is 5. So that would mean that the speed of the ball was 5 feet per second. Okay? Now, Speed, if you kick that ball and the ball went like this, if you notice in my definition, I put along a path at the end of it. With speed, you would measure the distance from here for where the ball started all the way along that path of the ball. And because we use 10 feet, that's what that is there. Now, there's another calculation that you can do, and that is velocity. Velocity is different from speed. It's the speed of something in a given direction. So if we wanted to know the speed of something as it went this way, we could do that. Except we'd have to measure from this point here. I'm kind of going out a little bit to here. See how that's different? When we were measuring the distance for speed, we went all along the path that the ball took. But now, when we're doing velocity, we're just going in one direction. So we're just wanting to know from in a straight line going in a single direction from here to here. So you don't get to do the whole path. So if that was like 8 feet, that would change velocity, right? Instead, you would have 8 feet and 2 seconds. And that would equal 4 feet per second. If you wanted to give this a direction, you could. But at this time, I'm not going to give it a direction. Okay? So that's the difference between speed and velocity. One is along the path, and one is just in a straight direction. Okay? So now we can actually go over some practice questions to see if you really got the concepts that we just talked about, okay? All right, let's do some practice questions. Let's see if you guys really understood the concepts of force and motion. All right, question 1. If you want to pause it, you can, and do the question yourself using your strategies. Let's read the question together. A wagon is pushed in a straight line. How would an increase in friction, I'm going to do increase in friction, on the wagon wheels affect the wagon? So we have to say how the increase in friction is going to affect the wagon. So what does friction do? Friction works against an object, so it slows it down. So we're going to read all of our answers, and we're going to look for the one that says that the wagon wheels will slow down. Okay? So A, it would cause the wagon wheels to move faster. We're going to go ahead and say no to that one. It would cause the wagon wheel to change mass. Friction doesn't change mass. The object is still the same. It would cause the wagon to change direction. It doesn't necessarily make it change direction because you have to have a force that goes in a different direction other than just against the object. It has to be a force that is in an opposite direction to change the direction, okay? So that's not a great answer. It's not a terrible answer, but I'm going to look for something better. Let's go to D. It would cause the wagon to slow down. Now, that's the one I would go with. So let's go ahead and cross out C, and we're going to go with D because D is the better answer. Friction slows something down, and eventually it stops. But if you don't have a force, another force, to change the direction, you can't really do that, okay? Let's go to number 2. A runner measured the time it took him to run 5 kilometers, or kilometers, whichever you like to say. So let's go ahead and just circle that. What can he calculate from the distance and time measurements? So what do we know? What kind of measurements can we come up with using distance and time? Well, we know that distance over time is speed. And also we could use velocity if we know the direction. So let's see if any of those things are up there. All right, A, we can't calculate direction. We don't have enough information. B, mass. You can't calculate mass. That's how much something weighs pretty much. And just knowing a distance doesn't help with that. Speed. Well, distance over time is speed. And then there's force. And what is force? It's a push or a pull. So not really able to calculate force using distance and time. So we're going to go with C, okay? And you see how it's just pretty much knowing the formula for speed that helps you get to the correct answer. Number 3. Which best explains, notice best is underlined, which best explains why a bicycle slows down? I'm going to go ahead and underline slows down when its brakes are applied. Why does a bicycle slow down when the brakes are applied? So what causes something to slow down? That would be forces acting on an object, right? Which would be the bicycle. And to slow it down, it would have to work against the direction that it's going. So let's see if we can find an answer that is close to that. So A, the brakes heat the rubber on the bicycle tires. So heat has nothing to do with it here, so we're going to go ahead and throw that out. And B, the brakes and energy add energy to the bicycle. That's nothing like what we're looking for, so we're going to go ahead and mark that out. C, the brakes increase the force of gravity on the bicycle. Do brakes increase the force of gravity? Do you remember what I said about gravitational force? That it's the same for all objects, right? And things just react differently based on its mass. So, having said that, this would be incorrect. It's not true, it's false. So hopefully our answer is D. The brakes cause frictional forces on the wheels of the bicycle. That's the best one because frictional forces work against whatever it is, whatever object, and it causes it to slow down. So that's our best answer. So I hope that you did well with that. That means that you understand the concepts. And we're going to do a couple more just to make sure that you got it, okay? All right, the next two problems. Number 4. A ball is kicked and rolls along a level field until it comes to a stop. What is the most, notice most is underlined, what is the most responsible for the ball coming to a stop? What causes objects to stop? That would be forces acting against an object. What forces have we talked about? We've talked about gravity and friction. So let's see in our answers if either one of those are there. Okay, so A is air. Air doesn't cause anything to come to a stop, really. Gravity, that's one of our forces. Mass, not necessarily, it's not the most responsible. And then there's friction. So we got gravity and friction up there. Now, you have to choose which one is the most responsible. Remember I said gravity is the same for all objects. So friction can vary. You're in a field, so it could be your surface. So I would go with friction because you're going to have more rubbing of objects than with gravity. Gravity is going to be the same no matter what, okay? So let's go with friction. But just remember that that's a little tricky if you don't really think it all the way through. Let's go to number 5. If a car is moving backwards, I'm going to underline that, that's important, along a road, can its speed be measured? So, speed can always be measured. Now, if this had said velocity, velocity would have been different because the directions would have been different. But with speed, we're just measuring along a path, okay? So let's take a look at our answers and see if we can find something that we like, okay? You can say, can your speed be measured? Yes, it can. And now here's the important part. Because the car does not have friction acting on it. Does direction have anything, whether you're going forward or backwards, does friction change on the same object? Either way, it's going against whatever the object's doing. So this is not a good answer. Whether you're going forward or backwards, whichever way you're going, friction is going to go the opposite way. So if you're going that way, friction is going to be rubbing against this way. If you're going that way, friction is going to be rubbing the opposite direction. B, yes, it can, because the car travels a distance in a certain amount of time. Now, they just told us speed, which is distance in a certain amount of time. So that's not incorrect. We're going to keep that. Remember, read all of the answers. No, it cannot. You cannot measure speed because speed can only be measured if the car is moving forward. Now, just in case you thought that was true, it's not. Remember, it's along the path, no matter what direction, okay? So this is not correct. It's moving in some direction, so you can measure it. All you need is a tape measure or some kind of tool that allows you to measure the distance. Next, D. No, it cannot be measured. Speed cannot be measured because the distance traveled backwards by a car cannot be measured. Now, we all know that's not true, okay? If it goes a distance, you can measure it, okay? So that's not true. So we'll go back to what we thought it was originally, and it is going to be B. So I hope that you did well with that and you understood the concepts. If not, go back and look at the video, ask your teacher, ask your rep family for anything that could possibly help you better grasp the information, okay? And I hope that you continue practicing your questions so that you can become faster at answering the question and getting more correct, okay? So, as I always say, it's important to exercise your mind as well as your body, and I look forward to seeing you soon.